So let's talk. Let's start off here talking about normal vectors. Now remember, normal is, when you talk about vectors, uh, we talk about orthogonal vectors. If two vectors are perpendicular, right? We have perpendicular lines, orthogonal vectors, and when we talk about orthogonal to a shape like a plane, we use the word normal. So today we're going to develop what's called the normal vector. So we think back to a result we proved last week. If the magnitude of a vector valued function is constant, then the function is orthogonal to its derivative. And so once again, that was just a vector way of saying if you're tracing out a circular arc, then your radius vector is orthogonal to your tangent vector. Okay, so we talked about that last week and we proved it using some properties. So we look at the unit tangent vector. So if our vector valued function is smooth, we can define the unit tangent vector. So the unit tangent vector is the direction of the motion. So it's the derivative, but the normalization of the derivative, I should say. So it's the derivative normalized. And we can think of that as the velocity divided by its speed. So we can also think of this as the direction of the velocity if we want. Okay. But since it's a hat, we know that, by definition, this thing is a unit vector. And so then we can apply that property. And since it has a constant length of 1, that means that it is orthogonal to its derivative. Okay. So if we think about what this would be doing in space, we got our curve, tracing along the curve, oriented. T hat prime is the direction we're going. So if you pick some points on the curve here, there's your T hat, there's your T hat, there's your T hat, there's your T hat. And if I wanted to figure out what does T hat prime talk about, well, we can go through the limit definition, and T hat prime would be approximately equal to T hat of little t plus h minus T hat of t all divided by h for a small value of h. So take a minute and make sure we're all good with that. Okay. So really, remember, this h is a scalar. So that means the direction of this can be approximated by looking at this vector. So if I take like a t hat of t, and then a t hat of t plus h, and then I just take this vector over to here and put it there, and then I look at the vector t hat of t plus h minus t hat of t. That's going to be this vector here. Okay. All right. So there's a lot of arrows up there, but that's going to be the red vector. I'll just do that as you go around. And so basically what this is going to do, if I think of t hat as the direction you're going, T hat prime is the rate of change of the direction you're going. It turns out this is the direction that you're turning. You follow? Right? So we're going to define n hat to be what you get when you normalize the derivative here. T hat prime. This is called the principal unit tangent vector. This is the direction you're turning. Okay. It's called the normal vector because it's orthogonal to t hat. It's a unit vector because we normalized it. And so in order to have a normal vector, t hat prime can't be 0, which means t hat prime has to be smooth. So since it's the direction you're turning, if you were if you're on a plane curve, like if you're in 2 space or 2-dimensional space, then n hat is always going to point towards the concave side of the curve. Which means if you're in a 2-dimensional plane, n hat is going to disappear at any kind of inflection point. Right? And if you think about it, that would make sense because an inflection point is where the second derivative is 0, which means the first derivative zeroes out, which means you would not have a non-zero tangent there. Or t hat prime, rather, would be 0 because you're changing concavity. All right, so let's take a look at this helix. We were looking at this helix yesterday, the circular helix, R of t. Find t hat, n hat, verify t hat's orthogonal to n hat, and then we'll plug in like a value for t, and then we'll check this out on GeoGebra. So we got cosine of 5t, sine of 5t, 12t. And we actually did a bunch of work yesterday. Like we found the derivative yesterday, but it's not too bad to do again. Welcome in. And we found the magnitude of the derivative. That was the speed. We found that this ended up being a constant 13. So for our t hat, once again, we just take the derivative, aka the velocity, divided by the magnitude, aka the speed. So we would just take this divided by 13. So we would just divide each component by 13. So let me know if that all makes sense. We good with that calculation? All right. Now we're going to get n hat. So the definition of n hat is we take the derivative of t hat and divide by the magnitude of the derivative of t hat. So this is the definition. So let's just start off with t hat prime. So we have to take the derivative of the vector valued function t hat. And the way we do that, we go component-wise. So once again, taking the derivative, don't forget your chain rule here. Derivative of sine of something is cosine of that thing times the derivative of that thing. So it's going to kick out a factor of 5. Switch over to cosine. Cosine's derivative is minus sine. It's going to kick out a factor of 5. And here the derivative of 12/13, that's just 0. And so then we can go in there and calculate the magnitude. And if you think about what's going on in this vector valued function, we got nothing happening in the z component. So all of this is happening in the xy direction. Do you recognize what this is going to do? Once again, you can kind of think polar here. Whoops, I wanted a different color. Let's do blue for polar. We can think of x as r cosine theta, y is r sine theta. Do you see what this is tracing out here? That'd be a circle, right? A circle of radius 25/13. And so if I take the magnitude of this and go through the calculations, you're going to get 25/13. And so to get n hat, I need to take t hat prime divided by its length. I would take that vector and divide by 25/13, which means I'd multiply each component by 13/25. So t hat prime of t divided by the magnitude of t hat prime is going to be each component times 13/25. So we get some cancellation there. Minus cosine of 5t minus sine of 5t and 0. And that's our n hat. Okay. So it's instructive to take a value of t, plug it in, get a point on the graph, and then kind of graph these things starting at that point to get an idea of what's going on here. So let's pick a t value. We want kind of a trig-friendly t value. I guess we could start with what? Like, let's just look at a particular t value. What's a trig-friendly t value? Yeah, let's do 0. So let's look at r of 0. So there's r of t. If I plug in r of 0, I get cosine of 0, sine of 0 times 12 times 0. So I'm going to get the vector 1, 0, 0, which corresponds to the point 1, 0, 0. Because once again, when we graph position functions, we assume that the initial point's at the origin. And then we'll fire up t hat of 0. That's the direction it's going. T hat at 0 is going to be 0, 5/13, 12/13. And then n hat of 0 is going to be -1, 0, 0. All right, so we're going to put this into GeoGebra, and once again, I'm going to show you how we can kind of get a picture of what's going on here. So the first thing I want to put into GeoGebra is the vector valued function itself, which we can enter as parametric. So cosine of 5t, sine of 5t, 12t. And we can kind of adjust here the parameters. Oops, let's move it over here. So here t's gone from 0 to 2 pi. We can just go put a minus 2 pi in there to get that. And if we want, we can kind of zoom out. We can look straight down here and see that we're getting a circle. So we are getting the helix here. We're interested in the point P 1, 0, 0. So there's the point P. And now we want to put on these vectors. So we got a vector T. This was the tangent vector. So once again, we can put a vector in, and we'll have it in, initially we can put it in standard position, and then I'll show you once again how we can shift it. What was our tangent vector? Uh, 0, 5/13, 12/13. 0, 5/13, 12/13. And then n is going to be the vector. Was it negative 1, 0, 0? Let me check that. Yeah, okay. Now what we're going to do is these are in standard position, okay? Okay, that's fine. But we're going to click these off because what we want to do is we want to have both of these start at the point P. So we can go into Tools and scroll down to the bottom here. Vector from point. So select a point and a starting vector. I guess we want these on temporarily. All right, so let's go to Tools again. Vector from point, so we can pick a point and a starting point and a vector. So we'll pick the point P, and then we'll pick a vector here, and then we'll do P and vector here. There we go. We'll take these off, and so we'll take this off here. There we go. And so we've got the, it'll create this, so P prime, translate P to P by N. So this starts at P, goes N, that'll give you the new point P prime, and then it crafts the vector. So let's graph this with red, say, so it's a little more vibrant, and then we'll graph. This is the translation of the tangent vector. So once again, we'll pick like blue or something, right? Just so we can kind of see it. And if I kind of zoom in here, hopefully you can see the tangent vector and the normal vector. So you see the relationship there? And it's worth doing this, to get a sense of what's happening here. On the next take-home, I do have you do a bit of GeoGebra work, just so you can see what's going on. Okay. So once again, the tangent vector, that's the direction you're going. If whatever force is acting on this object suddenly vanished, this would be the direction it would head, and then the normal vector does that. Okay, it's orthogonal to it. All right, example 2, find t hat and n hat for r of t is t squared comma t. Oh, did we verify? Oh, we got to verify that they're orthogonal. Let's do that. I forgot to do that. I apologize. Okay. So how do we verify t hat is orthogonal to n hat? So if I ask you, what's the quick way to check if two vectors are orthogonal, what do you do to find out? Yep, you take the dot product. And if they're orthogonal, the dot product should be what? Should be 0. So we go back to our t hat. Minus 5/13, 5/13, 12/13. Dotted with our n hat. And remember, when you take the dot product, you multiply the corresponding components and then you add their results. So when you multiply the x components, you got a negative times a negative, that's a positive. Sine of 5t, cosine of 5t. Multiply the y components, you got a positive times a negative, that's a negative 5/13. And look at that, sine of 5t, cosine of 5t. And then the z components, when you multiply, they zero out. Plus 12/13 times 0. So these cancel out, we get a 0 and we get a 0, boom, they're orthogonal. So this proves that they're orthogonal all the way down. So as you're traveling on this helix, you've got the direction you're going and the direction you're turning, and those are always at 90 degrees. Okay? So like if you're going on an on-ramp, if you're blasting down 90 and then you take the on-ramp, take the ramp at 44, as you're turning around, sometimes you feel that there's a force tugging at 90 degrees. I think that's called the centripetal force or centrifugal force, depending on your reference frame. That's the component of the force in the n hat direction. Right, so you might remember that from physics. All right, let's take a look at example 2 now. So r of t is t squared t. It's a two-dimensional vector-valued function. If we wanted to think about what this is, x is t squared, y is t. Right, so if we go back to our parametric days, I can plug y in for t. I get x equals y squared. And what kind of shape is this? Which of those conic sections is that? Do you know this curve? Yeah, it's a parabola. And since it's a positive y squared, it's opening to the right. So this is the graph of it. But as y increases, right, y is the t here. So it's a parabola with a trajectory. The trajectory is this. So this would be, kind of quoting Kepler's laws. This would be like a something coming into the solar system, spinning around, and then heading out. It's a parabolic trajectory there. All right, so we need to find t hat and n hat, show they're orthogonal. So once again, what's t hat? T hat is the principal unit tangent vector. So we're going to take r prime of t, which is a tangent vector, and then normalize it. So what is r prime of t? You take the derivative of each component. Derivative of t squared is 2t. Derivative of t is 1. And divided by the magnitude of that. So let's go down here and calculate the magnitude. How do you calculate the magnitude of a vector? It goes back to Pythagorean theorem. You square the components, add them up, take the square root. And let's make a quick check. Since we're dividing by this, we better make sure it's not what? It's not 0. And in fact, any value of t you plug in, you're going to square it, you're going to multiply it by 4, which is going to make it 0 or bigger. And then you're going to add 1 to it, which will make it bigger than 0, and then take the square root. So that's all positive. So here's our t hat prime of t. Would be 2t comma 1 over the square root of 4t squared plus 1. And once again, how do you divide a vector valued function by a scalar function? The same way you divide by any real number. You divide each component. Okay? Now to get n hat. Now the definition of n hat, that's the principal unit normal vector. That's the derivative of t hat divided by the magnitude of the derivative of t hat. Now we did a derivative like this last week. You may recall we went through, was it the exact same one? It may have been. And it got a little messy. You can do it. You can hit it with quotient rule and then all that other good stuff, right? But there's something about vectors in 2 dimensions, we pointed this out when we talked about orthogonality back in the day. But here's a nice little thing for 2-dimensional vectors. Let's say you've got a vector v with components a, b, and you want to figure out a vector w that's orthogonal to v. And remember, you can think of this direction, you're going over a and going up b, right? So assuming a and b aren't 0, you're on a slope that has a line b over a. If you want to get a vector that's orthogonal to this, you can think of like the slope of the perpendicular line is the negative reciprocal. So back when we were talking about orthogonality and dot product, we said, well, you could pick w to be one of 2 different things. You could basically switch the components and make one of them negative. So both of these vectors are going to be orthogonal to v. And you can check if you take the dot product of either of these with v, you're going to get 0. Remember that? That might not have been last week. I think that might have been the week before, because I think we did dot product the first week of class. Okay. But basically, so in 2 dimensions, you've got a huge advantage. Because instead of going through those derivative calculations, which could be complicated, you have basically 2 candidates. So what this means is that if you have a vector valued function t hat as an x of t, y of t, then your n hat really is one of 2 things. You can either, you switch the components and then make one of them negative. You can verify that if you take the dot product of either of these, you're going to get 0. And if you look at the magnitude of either of these, no matter which one you get, look what happens. You get a y squared plus a negative x squared, or you get a negative y squared plus an x squared. In either case, what's going to happen to that negative when you square it? Yeah, it's going to go away, and you're going to get this, which is the exact same as the magnitude of t, which is what? 1. So you can get n of t just by doing this switch. Now you will get 2 exciting options for n of t. So that's when we go back and say, well, n of t points to the direction that you're turning. So in 2 dimensions, that means we're pointing towards the concave side of the curve. So in our particular example, here's what we've got for t hat. We've got the 2t, 1 over the 4t squared plus 1. So our n hat is going to be one of 2 different options. You switch the components and you make one of them negative. You follow? And then to figure out which one it is, you go to the graph. So once again, here's the graph of the vector valued function. Notice we have a consistent concavity as we're going along here. So we could just pick a point. What's a convenient point to plug into this vector valued function? What's always a convenient point? Yeah. Oops, t squared t. So let's plug in 0. When t is 0, I get the origin. So boom, that's t equals 0. And now let's plug in, let's plug 0 into this. So t hat at 0 is going to be 0 comma 1. So that's my t hat. And so let's plug 0 into n here. So if I plug 0 into n, I'm going to get two options here. Option 1 is going to simplify to the vector 1, 0. Option 2 is going to be the vector, well, the opposite, negative 1, 0. So the question is, which of these vectors is pointing towards the inside of the curve? Which of these vectors is pointing towards the direction we're turning as we traverse this pass? The 1, 0 or the negative 1, 0? Which is pointing into the curve? So this would be my n hat. Geometrically, that'd be my n hat. It's orthogonal, pointing into the curve. Which is that? This one or the top or the bottom? Yep, it's the top one. And since there are no inflection points on this curve, right? These vectors are going to be consistently pointing in. You follow? There's no place where the concavity changes. I know that the top choice is going to be the choice for the entire curve. And so I can say, okay, well, I can say with confidence that n hat of t is going to be 1 over the square root of 4t squared plus 1, comma, negative 2t over the square root of 4t squared plus 1. Notice in this particular scenario, the x component is always positive, and the y component starts off as positive and then changes to negative as we go across the curve, and hopefully that makes sense. Because as I point these normal vectors, notice the normal vectors are always headed to the right. They always have a positive x component. But the y component here is positive when y is negative, and then it's negative when y is positive. So hopefully that all makes sense. So there's my n hat. And so if we wanted to show that t hat and n hat are orthogonal, once again you would take the dot product here. So that would be 2t over the square root of 4t squared plus 1, comma, 1 over the square root of 4t squared plus 1, dotted with the 1 over the square root of 4t squared plus 1, comma, negative 2t over the square root of 4t squared plus 1. And so you multiply the corresponding components, and then don't forget to add them up. So we're going to have a 2t times 1. The square roots cancel out. And then we're going to have a minus 2t. Roots cancel out. Adds up to 0. Any questions on finding the n hat this way? Or then checking that these vectors are orthogonal? And I'll leave it to you in the privacy of your own home. Since it's a two-dimensional thing, you can plot these things on the graph paper pretty easy. Pick a couple of points for t, plug them in, see the relationship. Okay. As you're moving through the curve, t hat's always the direction you're going, and n hat's always the direction you're turning. Okay, so if t hat is smooth, that means that you get a normal vector. So we can create now what's called the binormal vector. So bi means 2. Notice it's in terms of the cross product. Now this was on your last take home, right? And was this on take home 2, I think? If you take 2 unit vectors that are orthogonal and take their cross product, you get a third vector. Since this vector is the cross product, it's orthogonal to each of them. And when we go to find the magnitude of t hat is 1. The magnitude of n hat is 1. And since t hat and n hat are orthogonal, the angle between them is 90 degrees. So you can show that, that's how you show that b hat is a unit vector. Now once again, b hat being a cross product, we're technically living only in 3 space, although if you are in 2 space, you can sort of cheese your way into 3 space with the z component of 0. But let's find b hat here for our helix. So b hat is t hat cross n hat. So geometrically, you know, here's t hat, here's n hat at 90 degrees, and then using the right-hand rule, this would be b hat sitting up there. So now we've got like a portable 3-dimensional coordinate system. What was our t hat? It was what, minus 5/13 sine of 5t. Let me double check. Now here, this is how I can check. Let's go up here. So we'll just read those answers there. 5/13 cosine and then 12/13. And our n hat minus cosine 5t minus sine 5t 0. And so we would take the cross product of these 2 vectors. So it's been a while since we did a cross product. Might as well take the time to do it. That 0 will come in handy. Alright, I hat, eliminate the row and column the I is in. We've got a 0 there, minus a negative 12/13 sine of 5t. That would be a positive 12/13 sine of 5t. Minus j hat, eliminate the row and column the j is in. We get a 0 there, minus a negative 12/13 cosine 5t. So that's a positive 12/13 cosine 5t. Plus k hat times, eliminate the row and column the k hat is in. We get a positive 5/13 sine squared 5t minus a negative, so that would be a positive 5/13 cosine squared 5t. So we're going to get some Pythagorean magic there. What's 5/13 sine squared of 5t plus 5/13 cosine of squared of 5t going to work out to be? Five thirteenths. And so there you go. That's our binormal vector. And I'll leave it to you to go through these calculations to make sure everything's working the way it should. All right, we've done a couple of these calculations today already, so you can do that. So if we plug in 0 on this, so if I look at b hat of 0, That would be 0, negative 12 thirteenths, 5 thirteenths. Let's plug that into GeoGebra so we can see what the b is doing. So now we'll have the vector b rather. That would be 0, minus 12 thirteenths. You can see 0. And 5 thirteenths. There we go. And once again, we want to see B here starting at the point P. So we'll go up to our tools. We'll scroll down to vector from point. So we'll pick the point. We'll pick the vector. There it is. And we'll take this off. There we go. GeoGebra's getting a little wonky on me. I don't know. What do we want to make this? Green? That's an obnoxious green. There we go. There it is. And that's the B vector. So you can see with Tn and B, you have a portable three-dimensional coordinate system that follows you around. Okay. Now, if you look, any two of these vectors make a plane, right? Just like I, J, and K, any two of them determine a plane. And so that's what we'll talk about here, to be how we'll close out the day, is the TNB frame. Sometimes this is called the Frenet frame. Okay. There's more on that later. But here it is. So you got basically three planes. The osculating plane is the plane determined by t hat and n hat. So that's got normal vector b. So that's, and we'll see that's the plane of motion here in just a second, because we should have time to do the proof. The normal plane is the plane determined by the two normal vectors. So it's funny, the normal vector to the normal plane is actually t hat. So if we think of, like, as you're moving, like if you're walking, the plane that you're walking in, right, or the plane that you're of your body, that's the binormal plane. And then the rectifying plane is the one determined by t hat and b hat, and that's the normal vector n. Okay. So what B does, well, I guess we got to prove the theorem first. I guess we'll start tomorrow, I guess, with the theorem. But find the equation of the osculating plane when t equals 0. Okay, so this is the helix we're on. And so once again, the oscillating plane, the normal vector here, that's our b hat. So I would take b hat at 0 as our normal vector, which we just had, was 0, negative 12 thirteenths, 5 thirteenths. And the point is given by r of 0, which is 1, 0, 0. So that corresponds to the point P, 1, 0, 0. And we'll get the osculating plane, and hopefully, yeah, we should have a minute to graph it. And so how do you get the equation of the plane? You take 0 times x minus the x coordinate plus negative 12 thirteenths, y minus the y coordinate plus 5 thirteenths, z minus the z coordinate, and this is all equal to 0. So once again, this is an equation. I also saw, so remember that, I don't know, some of you had like W equals on there, which I don't know where you're getting at, but it's everything's equal to 0. You add them up, equal to 0. So you got a minus 12/13 y plus a 5/13 z is 0, and you could like multiply through 5z is 12y. I mean, there's all kinds of different ways to write this. Okay, that'd be your oscillating plane. So let's graph this and see what it does. See what it's how it's looking there. Z is 12/5 y. I think GeoGebra should be able to handle the 5z minus 12y. Let's see. Let's see if it can. Sometimes it's cool with it. Sometimes it's not. There it is. Boom. Okay. So you can see here. Let's see if I can turn off the axes here. Show plane. Show axes. There it is. So this is the osculating plane. So it's locally, the oscillating plane is the plane of the curve. It's the plane of motion. All right? And that's what we'll prove starting next time. So what we're going to prove next time is a very important theorem in physics. We're going to show that the acceleration of the object, has exactly two orthogonal components. One of them is the acceleration in the direction you're going, t hat, and the other one is acceleration in the direction you're turning, that's n hat. So that means that the plane of motion, because remember F equals ma, that's how the force is what generates the motion. The motion of this object lies in the osculating plane. So the fact that this plane the curve seems to sit in this plane near P, as P moves and T and N change and B changes, this oscillating plane goes with it, and that's the plane of motion. Okay?